another edition of William's Guide to Mathematics. We've been talking about latitude and longitude, and that is exactly what we will continue with today. But we've had 2 lessons on latitude and longitude. In our first lesson, we talked about the Earth. We also talked about features of the lines of latitude and longitude. And finally, we talked about how to locate position on the globe. In our second lesson, we continued from where we stopped in the first lesson by analyzing lines of latitude and longitude. And finally, we talked about how to deduce angular difference. All these will be the bedrock for what we are doing today. Meaning, if you are here to watch the video on latitude and longitude for lesson 1 and 2, it will be important to do that. And to get videos on that, subscribe to the YouTube channel now so that you can see videos from latitude, on latitude and longitude. Videos from William's Guide to Mathematics. By the way, let me tell you, it is a mathematics channel. And so we have other topics aside from latitude and longitude there. But for you to have an understanding of our lesson 3 on latitude and longitude, it is important to check on the videos for lesson 1 and lesson 2. Now, what do we have for today's lesson? We want to talk about how to identify problem involving distance along parallel of longitude. How do you know if a question is on distance along parallel of longitude? And secondly, we now learn how to solve problems involving distance along parallel of longitude. Now, let's start with identifying problems involving distance along parallel of longitude. What are the key points in identifying these problems? I mean problems regarding distance along parallel of longitude. The first thing is that for questions involving distance along parallel of longitude, the longitude must be the same. So we are going to have the same longitude. In our previous lesson, we said for us to analyze, we must have either the longitude or the latitude to be the same. For questions involving same longitude, we're of course talking about distance along parallel of longitude. Now, once we are able to identify that the question is on distance along parallel of longitude using the same longitude, the next thing is knowing the formula to use. The formula to use is a popular formula we already know. There's nothing so special about this topic, very simple. And what is that formula? The formula is the same formula we use for length of an arc. Remember length of an arc. What is that formula? Theta over 360 times 2 pi r. Remember in the previous lesson, lesson 2, I told you theta is the angular distance or angular difference. We explained how to get angular distance and angular difference in lesson 2. But in our example, I will also shed more light on that. We also have in the formula capital R. We are taking our R to be the radius of the Earth. If only you had watched lesson 1 video, you will notice where I talked about the Earth approximately being spherical in shape, and we are going to take the radius of the Earth in our own lesson to be 6,400. So our R is representing the radius of the Earth. Now, taking a look at this example 1, we have Alexandria 31 degrees north, 30 degrees east. Now, let us represent that on the globe. We have our globe in the form of a circle. We start by drawing the special line of latitude and longitude. What is the special line? The first one is the Greenwich meridian. We draw our Greenwich meridian from the north to the south. Then we also draw our special latitude called the equator. You can see that. So the dotted line is the Greenwich meridian, the red dotted line, while the blue is the equator. Now, let us now represent Alexandria. We have 31 degrees north. So 31 degrees north will also be blue because it is a latitude, a line of latitude like the equator. Remember in the first lesson, I said the latitude is relative to the equator. So 31 degrees north, not one of the equator, we place our 31. Let us label it 31 degrees north. The same thing we do for the east, 30 degrees east. That happens to be a line of longitude. that is going to be a red line. So we draw our 30-degree long. We draw it down from the north to the south. Now, having done that, we locate the point for Alexandria. Let's take Alexandria to be point A. We locate the point of Alexandria. Let's take that to be point A. You can see the point A being marked there. Then we do the same thing for Kigali. Kigali is 12 degrees south. We don't have 12 degrees south in our diagram yet. So 12 degrees south will be below the equator. So we place our 12 degrees south. You can see it there. We also have 30 degrees east. We already have 30 degrees east on the globe. So we don't need to draw that. All we need to do is now get the point of intersection between 12 degrees south and 30 degrees east. Here we have it. This is the point. So we can call that point point B. It is obvious now that what we have to be common is the line of longitude. And so we can take this to be a problem involving parallel line of longitude. So we can see that we are moving from position A, which is north, to another position B, which is south. So we are moving along the line of longitude. So it is easy to identify the line, the questions involving parallel lines of longitude. Now, we put our longitude aside. We are going to get our angular difference with the latitude values. In Alexandria, we have 31 degrees north and we have 12 degrees south, meaning we have different position, north-south. Remember, I told you that in lesson 2, anytime we have different position, we add together. So our theta will be 31 plus 12, simply because we have north and south, different position. So theta is 43. Now, having theta as 43, we now apply next our formula. Formula for distance AB will be theta over 360 times 2 pi r. We've just gotten theta as 43. 360 will remain 360 multiplied by 2. Our pi, as we know, is 22 over 7. And then our r, according to what I told you, is 6,400. So if you multiply all this, you will get 4,805.08 kilometers. We have another example talking about a plane moving from one point and flying to another point. Okay, let us represent this on the globe. We start by drawing our circle to indicate the globe. Then we draw the two special lines, starting with the Greenwich meridian, which is a special line of longitude, that is the dotted red. Then we also draw the special line of latitude, which is the equator. Now, after drawing these two, we now represent what we have in our question. We have 20 degrees south and we have 30 degrees east. 20 degrees south and 30 degrees east. Now, my 20 degrees south, let me start with that. That is a line of latitude. So it is coming south to the equator, 20 degrees south. I'm taking my latitude to be the blue line. So I'm going to use the blue line for easier identification. So you can see 20 degrees south, label 20 degrees south. We also have 30 degrees east. That is a line of longitude. East or west is a line of longitude. So drawing your 30 degrees east from the North Pole to the South Pole, that is 30 degrees east, labeled there. So we have the meeting point. You can call the meeting point, you can call it P. So let's take that as P. Now, we're told that it flies north for 4,000 kilometers. We're told that the plane flies northward. It's a northward direction. So what we'll have to do with the north? Of course, I told you we have north and south, east and west, meaning our north will only affect either north or south. So we have 20 degrees south. So the northward direction of the plane will only affect the 20 degrees south, meaning our 30 degrees east remains the same. Now, if it is flying northward, we don't know by how many degrees flying northward, but we know it is flying northward, meaning we might have to get our value of theta, which happens to be the angular difference. Okay, let's use the formula. Distance is equal to theta over 360 times 2 pi r. Our distance is given in the question as 4,000. Theta, we are looking for that, we don't know. 360 is a constant given in the formula, times 2. Our pi, 22 over 7. The radius of the earth, as we've been explaining, is 6,400. If you multiply 222 and 6,400, you will get the 2816 with 2 zeros with our theta. If you multiply the denominators, the values there, we have 360 and 7, that is 2520. Now, dividing the numerator and denominator, we give 111.75. Remember, we also have a theta there. Now, our theta will simply be 4,000 divided by the 111.75, and that is 35.8 degrees. If I should approximate that, that is 36 degrees. I told you initially that the northward direction of the plane will only affect the 20 degrees south. So if it is on 20 degrees south and is moving northward, 20 minus 36, that is minus 16. Having a minus 16 indicates that the plane would have crossed the equator. So we can conclude by saying that the new position for the plane is 16 degrees north for latitude, while it is 30 degrees east for the longitude. Finally, we talk about the third example. We have the plane moving from one point to another point. Of course, both points have their latitude and longitude. Before we do anything, let's represent this on the globe. We start by drawing our circle. You can see the circle is in form of, is representing our sphere, which is the Earth. Then we introduce the special line of longitude, that is the Greenwich meridian in dotted red, and also the special line of latitude, which is the equator. You can see it also in dotted blue there. Now, let us represent what we have in the question. 57 degrees north. That is a line of latitude, 57 degrees north. We draw that. I'm using blue also just to clarify it for clarity. And then we have 60 degrees west. 60 degrees west. Okay, 60 degrees west. You can see 60 degrees west on the diagram already now. Now the 60 degrees west and the 57 degree north, they intersect at a point. That means they meet at that point. That means that is the position of the plane where it is taking off from. So let me call that position, let me call it position X. And then I have another position which is 20 degrees north. You can see that on the diagram, 20 degrees north and 60 degrees west, which I already have based on the first position, so I don't need to draw that. So it's even obvious that what I have to be common between the two of them is 60 degrees west. I'm coming to that. Now the meeting point for this new position is this. You can see it. Let me label it Y. Now labeling the new position Y, I'm to calculate the distance from X to Y. Fine, the question is giving me the time for 3 hours and I'm being asked to get the speed. In our elementary mathematics, we know that there's a connection between distance, speed, and time. We already have the time, we are asked to get the speed, then let us first get our distance. We are familiar with getting distance. This is a question involving distance along parallel of longitude. Why? Because we have a common longitude. The common longitude in this case is 60 degrees west. We don't need that for our calculation, we only need it for our analysis. Now let's go to the formula. Distance is theta over 360 times 2 pi r. I want to believe you are familiar with the formula now. Our theta, how do we get our theta? Angular difference. So angular difference between 57 degree north and 20 degree north. The two are the same position, north. And we said for the same position, we subtract 57 minus 20. That is 37. So our theta is 37 degrees. So we have 37 over 360 times 2 times pi, which is 22 over 7, times 6,400, which happens to be the radius. If you multiply all this and divide, you will end up getting 4134.6 kilometers. Now look at this illustration where we have a triangle with DST. Of course, we have 1 at the top and 2 at the bottom. An easier way of knowing the order, the arrangement of these letters is just follow the order of the alphabet. We are dealing with 3 letters: distance, speed, and time. In the order of the alphabet, D comes first. So we have D, we have S, and we have T. So just follow the order of the alphabet. So D up, 1 will be up, 2 will be down. Now if I want to get my speed, which is down, my speed, which is down, speed is what I want to get from the triangle I have. It is distance up, time down, meaning speed equals distance over time. Again, speed is equal to distance over time. I've just calculated my distance as 4134.6. I will divide that with the given time, which is 3 hours. If I divide that, I'll get 1378.2 kilometers per hour. So the speed at which the plane was moving from the point X to the other point Y is 1378.2 kilometers per hour. Interesting. We've come to the end of another edition of a lesson on Williams' Guide to Mathematics. This is lesson 3 of the topic Latitude and Longitude. And so far in this topic, we learned how to identify problems involving distance along parallel of longitude. And we also learned how to solve problems involving parallels of longitude. We have done 3 lessons. If you are yet to subscribe, like I said earlier, do subscribe. Don't forget to practice some questions based on what we have done so far. The questions are there for you. You can take a pause before you check the answer. Solve those questions, then check with the answers to know how well you are making progress as regards this topic. Your comments are welcomed. You can always ask questions via the channel. You can send message to the WhatsApp number if you need any clarification or anything as regards this topic. We'll be glad to attend to you because we are concerned about you doing very well in mathematics. All we want you to do is to pass mathematics, and not just pass, we want you to pass very well. In passing mathematics, we're talking about P for perseverance, we're talking about A for accuracy, we're talking about S for simplicity, and we talk about S again for speed. All these 4 represent our core values as far as Williams' Guide to Mathematics is concerned.